So what we're doing here is we're clocking our fastball by throwing it horizontally off of a cliff. And we know how high the cliff is, and we use measuring tape or something to figure out how far it goes. Uh-oh, this drawing's terribly out of scale. It looks like our 45 meters is shorter than our 22-meter height. But anyway, to understand how to approach this problem, it's important to understand that the horizontal velocity that we throw the ball with doesn't change. It still has the same horizontal velocity the instant before it hits the ground. Well, after it hits the ground, of course, it comes to a stop. But the only thing gravity's doing is accelerating in the vertical direction. So gravity will end up giving the ball a y component of its velocity, but its x component will be the same before it hits the ground compared to right after you threw it. And you are throwing it perfectly horizontally with no upward or downward component to its initial velocity. And of course, well, its horizontal velocity wouldn't change if there was no air, but we're just going to pretend there's no air because that's what we do with these problems. So knowing that it's a constant x component of the velocity, then the average velocity would be that constant velocity, which would be the change in position over change in time. We already have a change in position, our displacement, which is 45 meters. So we just need to get a delta t somehow to put in this simple little equation here. And this is a lot like the Thelma and Louise problem. So we can come up with an equation with variables that we know that also has delta t in it and solve for delta t. So at this point, let's work from right to left. The first thing I did was I figured out what variables do we know? Well, we know its vertical displacement, the y component of the displacement over its travels, which was that 22 meters downward. And we also know that the acceleration entirely vertically, entirely downward in the y direction was the acceleration of gravity, 9.8 meters per second squared. And we know that if we threw it correctly, such that we were throwing it exactly to the left and not up or down, then we know that its vertical, the vertical component, the y component of its initial velocity was 0, but then the instant after we let go, gravity accelerated it downward, and it gained some component, and it ended up right before it hit the ground with a pretty decent y component of its velocity. But we don't really care what that is, because we can figure out what t is without knowing this, because of this kinematic equation. And since that initial y component of the velocity is 0, this term disappears, and we're left with this equation. We just solve for delta t, divide both sides by half ay to get this, and then and also take the square root of both sides. But this is exactly like we did in the Thelma and Louise problem to solve for the elapsed time. And once we found that time, we plug that value in up here, which is why, that's why we wanted to find the elapsed time, so we could plug it into this equation and solve for the velocity of the throw. Well, technically it's the x component of the velocity, but since the entire velocity was the x component, that is the magnitude of the velocity of your throw, which is, that's like 50 miles an hour. So don't quit your day job, you might not get drafted.